Hello, and welcome to Lesson 26 of this Introduction to Differential Equations with Wolfram U. In prior lessons, we have discussed the Laplace transform, how to use this transform to solve differential equations, as well as applying discontinuous and impulse functions like the unit step function and the Dirac delta function. We will now look at the product of Laplace transforms and consider a special quantity called the convolution. Let's take a look at an overview of this lesson. You might expect that if you multiply the Laplace transform of two functions, you would get the same result as if you were to take the Laplace transform of the product of those two functions. However, this is usually not the case. As is seen in the example here, we are using the Dirac delta as one function and sine of t as the second function. We can see in the example that the Laplace transform of the Dirac delta times sine of t is not equal to the Laplace transform of the Dirac delta times the Laplace transform of sine of t. For this reason, mathematicians have developed a different operation called the convolution that shares many of the properties of multiplication and also commutes with the Laplace transform. The convolution is a function defined by the integral over the product of the two functions under consideration, with one of the functions shifted by a certain amount. We will see that taking the Laplace transform of this integral results in the Laplace transform of one of the functions times the Laplace transform of the other function. Therefore, the Laplace transform of the convolution of two functions f and g is equal to the Laplace transform of f times the Laplace transform of g. We will see shortly how this can be applied to solving differential equations. Since the r dependence in the integral defining the convolution is integrated out, the convolution of two functions of t is also a function of t. The convolution of two arbitrary functions f of t and g of t is defined by the integral here, where the f function takes on the new argument of t minus r, the g function takes on the argument of r, while the integral runs from 0 to t. The convolution operation shares some common properties with other more familiar mathematical operations like addition and multiplication. Interestingly, the convolution operation is commutative. This means that when calculating the convolution of two functions f and g, it doesn't matter which function takes the argument of t minus r and which function takes the argument of r. Convolution is also distributive, so the convolution of f with the sum of two functions g and h is the same as the convolution of f and g plus the convolution of f and h. In a similar way, convolution is associative, which means that we can group the convolution operation in any way as indicated by the parentheses in the equation here. The convolution theorem states that the Laplace transform of the convolution of two functions is equal to the product of the Laplace transform of the two individual functions. Let's demonstrate this equality with an explicit example using the two functions sine of t for the f function and e to the minus t for the g function. Calculating the convolution can be done with ease using the integrate function and the definition of the convolution of two functions. With the convolution obtained, calculate the Laplace transform of that convolution. This result gives the Laplace transform of the convolution. We will now show that this result is equal to the Laplace transform of the product of the two functions. To prove the convolution theorem, we need to show that the Laplace transform of the convolution of sine of t and e to the minus t is equal to the Laplace transform of sine of t times the Laplace transform of e to the minus t. Calculating these two Laplace transforms and their product is an easy task in the Wolfram language. Comparing the result we found on the previous slide and this result shows that the two expressions are equal, which proves the theorem in this case. Therefore, the Laplace transform of the product of sine of t and e to the minus t does equal the Laplace transform of sine of t times the Laplace transform of e to the minus t. We will now discuss why this result is useful mathematically and how it can be applied to differential equations. Consider finding the Laplace transform of the integral quantity here. This integral is of the same form as in the definition of the convolution theorem. Therefore, by noticing that the t minus r squared term must correspond to the function t squared, and the sine of r term must correspond to the function sine of t, we can use the convolution theorem to write the Laplace transform of this integral quantity as the Laplace transform of t squared times the Laplace transform of sine of t. We can calculate this product of Laplace transforms explicitly right here. We can calculate the Laplace transform of the integral to show explicitly that the two calculations are identical. Let's use the convolution theorem to find the inverse Laplace transform of the function here. It may not be obvious at first, but it turns out that this function is the same as the product of the Laplace transform of cosine of t with the Laplace transform of sine of t. Since the product of the Laplace transform of two functions is equal to the Laplace transform of the convolution, we can take the inverse Laplace transform of the right-hand side to conclude that the inverse transform is equal to the convolution of cosine of t and sine of t. Calculating this convolution gives the inverse transform of the function. We can confirm this result by calculating the inverse transform with the Wolfram language inverse Laplace transform function. In this example, we will find the inverse Laplace transform of the function here, where phi of t is an arbitrary function of t. Recognizing that the 1 over 1 plus s squared part is the Laplace transform of sine of t, we can see that the function above is equal to the Laplace transform of sine of t times the Laplace transform of phi of t. Therefore, using the convolution theorem, we can calculate the inverse Laplace transform by calculating the convolution of sine of t with phi of t. Consider the second-order non-homogeneous differential equation here, where the non-homogeneous term is now an arbitrary function of t. A set of initial conditions on the solution and its first derivative at t equals 0 are provided as well. To find the solution, first find the differential equation in the Wolfram language. With the equation defined, apply the Laplace transform to the entire equation. We can now use the initial conditions to replace the y of 0 and y prime of 0 terms that appear when taking the Laplace transform of the entire equation. We now have an expression involving the Laplace transform of the solution and the Laplace transform of the arbitrary function phi of t. Solving the expression on the previous slide for the Laplace transform of y at t gives the following result. We would like to take the inverse Laplace transform to find the solution. Recognizing the 1 over 1 plus s squared term as the Laplace transform of sine of t, we can write the Laplace transform of y at t as the product of the Laplace transform of sine of t with the Laplace transform of phi at t. The solution is then obtained by using the convolution theorem, since the transform of the product of two functions is equal to the Laplace transform of their convolution. Therefore, the solution to this initial value problem for any function phi at t can be obtained by evaluating the integral here. Let's solve another second-order non-homogeneous differential equation with a general forcing function phi at t and a set of initial conditions. The process to solve this equation is the same as we have done several times in the course now. Define the differential equation in the Wolfram language, calculate the Laplace transform of the differential equation, then replace the initial conditions with their respective numerical values. Now we have an equation involving the Laplace transform of the solution that can be solved. Solving the equation on the previous slide for the Laplace transform of y at t gives the result here. We would like to take the inverse Laplace transform to find the solution. By recognizing that the 1 over 1 plus s squared part on the right-hand side is equal to the Laplace transform of t times e to the minus t, we can write this as the product of Laplace transforms here. Therefore, using the convolution theorem, we can write the solution as this. As a result, the solution to this initial value problem for any function phi at t can be obtained by evaluating the integral here. Let's solve the equation here, which has the same left-hand side as the previous example, but the phi at t function on the right-hand side is now a Dirac delta function with the argument of t minus 3. Using the integral form for the solution we found in the previous example, we can calculate the solution immediately. Comparing with d-solve value, we see that the results are identical. We can also see the effect of the delta function in a plot of the solution. The delta function is applied at t equals 3, which is evident in the solution as the function suddenly jumps at that point. In this lesson, we have introduced a new operation known as convolution. We have seen that the convolution of two functions is defined by the integral here. An important result is the convolution theorem, which states that the Laplace transform of the convolution of two functions is equal to the product of the Laplace transform of the two individual functions. We then use the convolution theorem to show how we can solve many different types of differential equations in a general manner.